Okay, my name is Mohammad Reza Bilesan from Hydrometallurgy for Urban Mining Research Group. My supervisor is Associate Professor Evelina Repo, and I'm going to present the topic Utilization of 3D Printing in Separation Technology. Our project is part of Regold AM project, and it is funded by Academia Finland. As introductory, I'm going to start with explanation of electrochemical removal of metals, electrode deposition, which is a well-known method to produce in situ metallic coatings, which can be explained as a process that can uses an electric current to reduce dissolved metals cations so that they form a thin coherent metal coating on an electrode. Therefore, cell performance is highly related to the materials selection and designs. Here in the schematic, we have the electrochemical fellow reactor, which it has the cathodic chamber and anodic chamber, and the metal can be coated or can be separated from the solution to the cathode, and we have the anodic chamber, which the anodic reactions are going to be performed. Therefore, for instance, cathodic reactions are highly dependent to the anodic reactions. So if we can increase the anodic reactions, we can therefore have a better removal of metals in cathodic reactions. Okay, as we can see, we have subtractive manufacturing and additive manufacturing for producing the anodes for the electrochemical cells. As a comparison, the additive manufacturing can have fast prototyping and up to 84% lighter waste production in comparison to the conventional subtractive manufacturing. So this can be a significant advantage of the additive manufacturing for manufacturing these electrodes. As an introductory, I'm going to present what is additive manufacturing. Physical structures are designed from a 3D CAD data directly, usually layer by layer. This layer by layer production can be really important for anode. As you know that we have 3D slicing in designing the printing path, filling density angle shells, and storing the sliced file in G-code format, which later it can be 3D printed layer by layer, and therefore this layer by layer production can increase the surface roughness of the final product. So for developing high performance anodes, additive manufacturing allows us to have a variety of properties associated with geometry, rigidness, porosity, and size. These items are so important. For example, we can have highly porous. We can have a free selection of geometry, size, and shape in micrometer or even in nanometer. Or we can have superior mass transport characteristics and even corrosion control. So the choice of precursor materials and the type of 3D printing technique allow to control over these properties. So the electrode designs that are being used these days as a high surface area electrodes are presented here. Two examples. One is the porous sponge or foam metals. Here in the picture, you can see the nickel foam electrode on top. And nickel foam electrodes, they can have open pores or closed pores, which are uneven sizes and shapes of the pores. Or in the second picture, in the last picture, the titanium ruthenium iridium mesh structure, we have the limitations for complex designs. They usually they combine with woven rods together, and they have these final shapes, which are we have the limitations for complex design. But here, by 3D printing, I presented the CAD design of our generated electrode. We can have high surface roughness, which provide a high surface area by this layer by layer production. Here in the picture, STM image of a 3D printed structure are presented. The top view or side view You can see that equal size and shape of the pores. It can provide a convenient and better distribution of electric charge. And therefore, for the flow reactor cells, we can have a better distribution of electrolyte toward the targeted surfaces. So here I presented a short summary of our results. The electrochemical active surface area can be calculated, can be studied. A simple shape plate electrode was compared with a 3D printed one, and the electrochemical surface area is the main parameter that is affected by an electrochemical reaction. The anode, which has more electrochemical surface area, demonstrated a higher reaction on their surface. So to evaluate the electrochemical surface area, the different cyclic voltammetry scan rates were measured in the non-Faradic zone. Here in the picture, the cyclic voltammetry of plate and 3D printed electrodes are presented. The upper one is attributed to 3D printed electrode, and the lower part is the result of the plate. As you can see, we could get higher currents, much higher currents than plate by these 3D printed electrodes. As an introductory, I can say that the non-Faradic current, which the results are here presented, are so much dependent on the surface area of the electrodes. That's why we consider the non-Faradic current to study the electrochemical surface, active surface area. According to the electrochemical, the ECSA of the lattice structure and the plate, the electrochemically active surface area of the scaffold is 42 times more than the plate. Here you can see the picture, the current densities at different scan rates are illustrated, and you can see that much more difference. The 3D printed electrodes has much more current than the plate, and that means that all electrochemical reactions can be improved very well. Refer to that the first slides that we presented. I discussed that we can increase the anodic reactions, therefore we can increase the cathodic reactions by increasing these anodic reactions. As corrosion control, according to the polarization result of the different aqueous alkaline solutions, the corrosion rate of the lattice structures was acquired. Here we have the picture of corrosion rate in MPY, milli-inch per year, extracted from polarization curve. And it is possible to control corrosion at 0.08 multiply 10 to power minus 8 nanometer per year, which is so significant also. Here we have the structural difference of the lattice structure electrode after a tough condition. The picture is the optical microscope picture before electrochemical test, and the right one is after electrochemical test. The tough condition is that voltage was 5 volts, time was 600 minutes, and sodium hydroxide 1.5 molar was used as electrolyte. You know that, for example, for usual separation technology, we usually use 1 to 2 volts potential, and the time would be around, for example, 1 to 4 hours. But here we increase the time and voltage to see what will happen, and also you can see that the structures are well disciplined. Still, it could take this disciplined structures at the end of these tough conditions. In summary, additive manufacturing can provide a faster and more affordable process. I mean, 84% less material consumption, high surface roughness, large variety of discipline, shape, and size selection, and improved flow cell performance can be applied for the anodes. The electrochemical active surface area can be increased by 40 times than a simple plate anode. The low corrosion rate can confirm the feasibility of the consumable low-cost anodes in a logical long-term durability. Thank you very much for your attention.